But yeah, so today we're going to talk about this paper from recent ATC, using ATC, RRC, responsive replicated containers. So I will kind of say it right away. I am not sure, like, I fully understand the reason for doing this and for doing like similar approaches. But I thought that the paper was decently interesting. So maybe someone can convince me of an actual like good reason to things like that. But yeah, so let's assume that we have some kind of application that is so like mission critical that we don't want it to fail, right? So this application, well, because we don't want it to fail, we have to protect it from the failure somehow. And typically we do it by replication, right? So we've studied like a lot of replication stuff in this reading group, mostly as it relates to databases, and not just like any arbitrary applications, right? But here we have an application that is otherwise not designed to be replicated, right? So it's like a single machine application, but you need to make sure it doesn't fail, right? So kind of one way you can approach the problem is essentially have a second copy of this application and do everything twice, right? So as a user, you may interact with the first copy of application, interact with the second copy of application, and just like do everything twice. There is a problem with this approach, of course, is that it really relies on the fact that like all of your interactions are going to be deterministic, and everything else that happens in the application around your interaction is deterministic, right? But an actual like computers, they're not very deterministic, right? We have all kinds of things going on, like different clocks, clock rates, go up and down and things like that. Schedulers, racing between cores and threads, and data races, and so on and so forth. So all of that makes this kind of more complicated. So now we need to record, not just like have the copy the input or do everything twice on two copies of this application, but we also need to somehow make sure that we preserve all of this non-deterministic state that happens in one application into the copy of another. Right, so this is kind of how it will work in this approach. So we'll have server one, right? So maybe some requests are going to come into server one, and it will do some stuff, well, we also have server two, which is our like a backup copy. And the server two will need to receive the same request, right? It will need to receive the same request. But for it to do this request, it needs to know like everything that's non-deterministic that may have happened right here. So what will actually happen is, this server one is going to send all of this non-deterministic like commands, all the log of everything that happened non-deterministically to server two. So server two can replay the original input and interleave it, like every changes that happened, every non-deterministic commands that were executed on server one, it will just take the results of them from the server one from that copy and kind of replay the application, right? So another command comes in, it will be processed and get here, and that non-deterministic stuff gets here, and essentially we have like a duplicate copy of the application. So this, in a mind of the paper authors, this works at the level slightly above application, like a container or virtual machine. So we're actually replicating like more than just an application process. It's like a container, right? And they say that this approach, which is really a primary backup replication, right? They say that this approach, has a few like downsides. Obviously, if you cannot record all the non-deterministic actions, like if you missed something or some action that you thought was deterministic happening on machine one, but it actually is not deterministic, then you lose the risk of having the server two to be in a divergent state. Right, so that's one problem. And the second problem they say is, well, because server 2 is running an exact copy of this application, it actually needs to use as much resources. So your like resource overhead is at least twice the amount of resources compared to just running it on one machine. So they say, okay, well, there is a different approach, right? So instead of doing this streaming of all the non-deterministic operations and all the inputs and like essentially running two applications side by side, this fixing non-determinism, we can just ship frequent snapshots, right? One thing I forgot to mention here is, of course, the client needs to get a reply from an application, but you can only get this reply from an application from server 1 after the backup copy acknowledged that it has replayed this command perfectly fine. So the client will see the reply only like a little bit later, right? So that is obviously if we want to make sure that we don't lose any of the operations in case the machine fails, the primary fails. So the second approach that they talk about that people apparently have been using is using snapshots, right? So we have a server 1, it runs for some time, have server 2. So if we have client requests coming to server 1, the server 1 is going to do these client requests. It's going to like do all of them and buffer the outputs, right? So it's not going to reply to the client right away. At some point, a snapshot is going to happen, right? So we're going to snapshot the state of server 1, and we're going to ship it to server 2, and the server 2 is going to apply the snapshot. And once it's applied, it will tell the primary, hey, I'm caught up, and now the primary can reply to all the clients. Right. So this like purely snapshot driven approach, it avoids the non-determinism issues, right? So we just send the snapshot, the server 2 just essentially stores all the snapshots until they need it for later use, right? It also avoids this need to have server 2 actually running the entire application, because while the server 1 is still alive, while the primary is running, the server 2 can be this kind of passive replica that doesn't actually run application code, just stores those periodic snapshots. So it can use a lot less resources while it's in this passive role. Well, the downside of this, of course, is we have a very high latency, right? Because we need to essentially take a snapshot, like wait until we take a snapshot, move the snapshot to server 2, apply it, store it on server 2. Server 2 needs to acknowledge it back, and then we can reply, right? So the latency at which clients will learn of their operation completion really depends on how frequently we can do the snapshots and like perform all of this operation. And obviously taking a snapshot of the entire like container is not a super quick thing, so we don't want to do them too frequently. And the paper says that like in practice, we can take snapshots every like 10-20 milliseconds or so. So that's kind of what the existing systems are doing. And they say, okay, we don't like it. We don't like the latency that is like large for the snapshot approach. We don't like the resource overheads that are in a primary backup and this like reliance on making sure that we capture all the non-determinism. So let us do something about it. And what they propose is a system that again consists of 2 servers, right? So the primary S1, the backup, so yeah, this 2 servers. The clients, when they talk to the primary, at this kind of container boundary, right? So this operation, this request is going to be intercepted and sent to the backup. the backup is going to record this operation and then tell the primary, okay, this is what you need to do. The primary is going to carry out the operation, just like in the primary backup kind of situation, but we already have the operation recorded. It will ship all those non-deterministic stuff that may have occurred, all the syscalls and stuff like that that are potentially non-deterministic. It will ship it to the server 2, and the server 2 is going to record those, but not like replay them, right? So just keeping the original request, keeping the the log of non-deterministic events, and as soon as it acknowledges that, we can reply back to the client, from the primary. Here I think they also send the result of the execution just in case. So this latency is smaller than the snapshot approach because there is no snapshot, right? There is like a little bit of going back and forth, but we're not taking like any big snapshots. And if we continue doing this, very long, at some point we actually will make the snapshot, right? And we'll ship the snapshot. Again, we'll store the snapshot on server 2, and at this point we can discard all the logs that were from the previous snapshot, right? All the non-deterministic logs that were not for all the stuff not captured in this snapshot, right? So whenever the primary fails, the secondary, the backup, can take the latest snapshot and replay, any of the non-deterministic logs on top of the snapshot, get its state up to the most recent state of the application, and continue working. There are some other failure modes that the paper talks about, like what if the backup fails instead of the primary, because we rely on like recording all of this, and they just say we're going to have a failure detector, and we're just going to switch this S1 into operates in kind of standalone mode until the backup can recover. So that's kind of the solution at the very high at the very high view. So it combines the snapshot solution, and it combines the primary backup solution together to provide lower latency and to avoid running the actual application on the machine S2 until you actually need it. They obviously run a lot of experiments and evaluations, and show decent results. Obviously there are overheads, and they will depend on different applications, but supposedly based on the evaluation, the results, like the overheads and the performance of this approach is better than the snapshot approach, right? So just a regular frequent snapshotting, and that was their main benchmark. I don't think they benchmark against the purely primary backup replication approach. So obviously with their approach, the latency is much smaller, like 2 orders of magnitude, because they don't have to wait for the snapshots, which takes tens, dozens of milliseconds. Their overhead still obviously present, but supposedly also smaller than the purely snapshot approach, and that is partly because of some other things that they talk about in the paper on how they take those snapshots. They don't just take the snapshots when they need to take the snapshot. They don't just they don't stop the container for very long. They stop it for a short amount of time, make like a soft copy, resume the original container, and make a snapshot from that copy of the container. So there are some overheads on copy on write memory and stuff like that, but the goal is they don't stop the actual container for too long. The paper talks about a few other interesting things, like non-determinism in multi-threaded applications, right? So apparently that was a bit of an issue at least in some of the workloads that they benchmarked against, where because the application is multi-threaded, right? So if S1 is multi-threaded, and we make some kind of system call on one thread, and then maybe another one on another thread that's much bigger, right? And then we ship the results of these system calls to server 2 for replay. Well, the replay just replays the results, right? So while these two were kind of concurrent, okay, probably a better example here. Let me go back. Now, if this one is very long, if this one started later but very short, yeah. So the point is, I guess they can be reordered. I am having a brain freeze to try to come up with a trivial example of how they will be reordered. But the idea is, you execute it for very little amount of time here, right? You just like instantiate, like replaying the result. You have the result of each of the systems calls, right? So yeah, the way they play out here may be in different order than there. And if your application has like data races, if your application is badly designed, that can cause problems. So there are like a whole discussion on this topic. Yeah, I think I will stop my presentation at this point.